non-relativistic elastic collision in 1D, one dimension, and two masses. So, and the main tools we're using are conservation of momentum and conservation of energy. So we have conservation, momentum. Momentum is always conserved. And so the reason the momentum is always conserved is because the only changes in momentum take place during the actual impact. And those forces are all internal between the bodies. And so the total momentum for the entire thing is conserved. And the reason the energy is conserved, and this is the kinetic energy, is because it's elastic. So when we say it's elastic, that's another word, that's another way of saying the kinetic energy. The total kinetic energy before is equal to that afterwards. So the collision we looked at is we had an initial velocity 1. So this is particle 1. So I is initial here, and in the lab frame it was moving at some initial velocity. So that's v1I, and then it hits something else which has a different mass m2, and its initial velocity we set it to be initial equals 0. We set it to be 0. So in the lab frame, this guy comes and hits that guy, and then the first one bounces off. So afterwards, this one is moving this way with V1 final, and this guy is moving that way with V2 final. And because this one is if this one's more massive than that one, then this one is going faster than this one. But it's not as fast as it initially was because of momentum conservation. So that's in the lab frame. And we came up with using conservation of energy and momentum, we found formulas for these two guys. So let me remind you what they were. So V1 final was m1 minus m2 over m1 plus m2 in terms of the initial velocity, and V2 final was 2m1 over m1 plus m2 V1 initial. And one of these, that was what we derived last time. So right at the end of the lecture, I was taking limits. So let's take the limits again. And this is in what I would call the lab frame. So one of the things I'm going to do today is go back and forth between lab frame and center of mass frame. So we'll find the center of mass velocity, and we'll change all the velocities so they're with respect to the center of mass. And then we'll look at the collision in that frame, and then we'll solve it again. And then we'll transfer back into the lab frame, and we'll show that there are two ways you could solve the problem by going into the center of mass frame and solving it, and then transferring back. Often that's easier, actually. So working in the center of mass frame has some advantages to working in the lab frame. You can always solve the problem. If you can solve the problem, you can always solve it in any frame. But sometimes the calculation is easier if you think about it in the center of mass frame. So before we do that, let's just take some limits. So one limit is, what if the two masses are the same? So let's take m1 is equal to m2. In that case, I'm just going to plug into these formulas, and I get v1f is equal to 0, and v2f is equal to 2. So this is 2m divided by 2 is equal to v1I. Okay. So in this case, the final velocity of the first one is 0, and the final velocity of the second one is the same as the initial velocity of the first one. So what actually is happening is this guy comes in, and he's hitting this one, and then afterwards he's fixed, and then the second one leaves. So I guess I'll draw it this way. So we can even draw him like that. And so this guy comes in, hits that guy, then he stops, and this one keeps moving like that. So so that's not necessarily surprising. I think of a billiard ball and a billiard table. Like if you're playing pool and you hit a ball and it hits the other ball, it stops and the other ball keeps going. So it's not necessarily unexpected. The other thing that's maybe you're used to seeing this happen is this toy that's called Newton's Cradle. So next on Thursday, actually, I think we're going to have a demonstration. We'll have a Newton's Cradle to play with in the classroom. So I have the Newton's Cradle. It's like a post here, and then you have on a string a mass, and then there's another mass with another string, and another mass with another string like this. So this is called Newton's Cradle. And it's a toy, right? And so if you pull this one back, it comes out and it hits the next one, and then this one hits that one, and then this one hits that one, and then this one comes out with the same velocity that you hit the first one with, and all the rest stay fixed. So some of you guys, so if I pull this one back, then this one moves and the rest stay fixed. So many of you have seen this, and we'll see this in class. So let's look at Newton's Cradle again. So I described it with this one hitting this one, and then this one hitting that one, and then that one hitting that one. So they're all just like this limit, the M1 goes to M2 collision, where we have an incoming velocity and the other one is fixed. But what happens if I glue these together? So I'm actually going to do 5 here. So let's put another one here. I'm going to glue these 4 together, and this one's going to hit all 4 at the same time. So let's go back to our formula. So V1F is equal to M1 minus M2 over M1 plus M2 times V1 initial. So if I plug into this formula, but now M2 is not equal to M1, M2 is equal to 4 times M1. So I have M1 minus 4 M1 over 5 M1 V1I. And this is equal to minus 3/5. 1 minus 4 is minus 3/5 V1I. And I can solve for the second one too, V2F, the velocity. And now I'm assuming these are all glued together. So what's the velocity of all these guys? So this is 2 M1 over 5 M1, because it's 2 times the first one plus over the sum of the of the 2. V1I, which is equal to 2/5 V1I. So I need to solve that. So it's equal to 2/5. So the exact numbers are not the thing that I wanted to point out. But I wanted to point out that the first one bounces back, and the 4 together move at a velocity that's not the same as the first one. So when you actually think of Newton's Cradle, we think of this one coming in and that one coming out. The only reason that works is because there's a little bit of space between each mass here. And that's purposely done. When you look at the toy, that space is very carefully adjusted. It's hard to see. But if there weren't spaces between each one of them, then when this one hit, it would be as if it were hitting 2 at once. And then you would get different velocities, and you wouldn't have that chain reaction that you don't actually see very well. So that's just something to keep in mind. The actual Newton's Cradle has got this careful design thing that most people don't notice and if these strings slip, you'll notice it doesn't work the way you want it to work to show this chain reaction. Yeah, so that this example of Newton's cradle, it looks very simple, but if you think about one-dimension stacks of different balls or something, so even that problem of what's the behavior of a series of collisions in a long chain of masses, that's actually, you can get some pretty interesting phenomena, like things that act like shocks, and what happens if there's imperfections, if you have a pulse moving through a chain of masses, depending upon how they interact. So that problem, actually, there's a series of math literature studying and experimental literature studying rows of masses that can interact in various ways. So even things like, actually, so one thing that's kind of fun to play with in the lab is you know, if any of you guys ever played with hydrogel beads, those are for plants, and they're very elastic and they're wet. If you put those in a row and tap them, they act a little bit like Newton's cradle. But you can put them all in a row and look and see how a pulse travels through them all, through a series of them. It's not a very expensive experiment to run. But predicting the outcome horizontally, if there's no friction, it's not easy necessarily, even in that setting. If it's vertically and you've got more gravitational force from the weight of all of the ones above it, that's even harder to predict. And if you look at the problem of, let's tap it with a pulse and it's going up and the top one could come off the top, that I have not seen a lot of work on. So even this particular problem, series of masses undergoing elastic collisions, not necessarily 100% elastic, can be interesting when you think about chains of them. Okay, so that's Newton's cradle. We'll have a demonstration next week. So so again, we're still talking about this elastic collision in one dimension. So let's now go into the center mass frame. So, yeah. So that's what I'm going to talk about. So, I used the V1I in the lab frame. This was the initial velocity of the first particle, and we had V1F and V2I and V2F, like this. So let's use U1I and U2I and U1F and U2F. These are to be the velocities in a frame moving with the center mass. So this is the center of mass frame. So I'm just going to use that to remind you that we're working in this other frame. So in the center of mass frame, the center of mass velocity is 0. So remember, the way we compute the center of mass velocity is the sum over all the particles, mi vi over m, that versus that's the total mass. So in the center of mass frame, this is going to be 0. So I can move this to the other side like this. And in the center of mass frame, this is going to be 0. And now I'm going to put these U's to make it clear that the center of mass, that this is the center of mass velocity. So let's rewrite this. So this is M1U1I plus M2U2I, and that's before the collision. So those are the initial velocities, and that's 0 because we're in the center of mass frame. And we could also write this out for the final U2I plus M2. This is U1F, this afterwards, U2F is also 0, okay? Because this is the center of mass. Because we're in the center of mass frame, this is actually the total momentum. So you can think center of mass frame, the total momentum is 0 because the velocity of the center of mass is 0. So this is total momentum before the collision is 0, and total momentum after the collision is also 0. So this is actually equivalent to conservation of momentum in the center of mass frame.
Professor Quillen, is on the second line where you have M2 U1F, is that supposed to be M1 U1F?
Yes, it is. Well, you know what? I'm really happy that you can see that. Good. Yes, that's what I meant. Thank you. Okay, actually, you know what? I'm noticing that I don't have the video up. That means the recording may be missing my view. Okay, well. Okay, so okay, good. So that was conservation of momentum. Now let's look at kinetic energy. I'm just going to leave this up. So kinetic energy, because it's an elastic collision, kinetic energy before and after the collision is the same. And it's because it's a two-body problem, we can write, and we're in the, so remember the two-body problem, we can write kinetic energy as a relative velocity, u1i minus u2i squared, plus a translational term. But because we're in the center mass frame, the translational term is 0. So there's no extra term. And this is the reduced mass. So remember, the reduced mass is the product of the masses divided by the sum of the masses. Okay. And this is the same, because it's an elastic collision, this is the same before and after the collision. So I have U2, U1i, U1f minus U2f squared. So sometimes it's helpful to write. So there's 1/2 mu on both sides, so we can get rid of the 1/2 mu pretty easily. And sometimes it's convenient to write this as U1i plus U2i times U1i minus U2i, because this is just a no, actually it's not right. You can't do that. You can't do that because this is an actual square. This is just 2 times. So we could instead do this, except that you have to be careful with the signs. Sorry. Sometimes in these problems, completing the square actually helps you solve it. In this case, you just do that. So the difference in velocities before is the same as the difference in velocities afterwards. Okay, so I have this condition and I have that condition. This lets me solve for U2i in terms of U1i, and so I can put that in here. And this condition lets me solve for U2i in terms U2f in terms of U1f. So if I want to, I can put that in there. And then that would then give me, yeah, so I can, so we can do that actually. And what we've, so let's do that. We'll place this will get rid of U2i using this condition. So U2i is M1 over U1i divided by M2 with a minus sign. So let's do that. So I'll put that here. So I get U1i minus M1 over M2 U2i, and then this, there's an absolute value, but I could also have a square. And I'm going to replace this with U1f. So I have U with an absolute value, U1f plus M1 over M2 U2f. Actually, there's a plus sign because the the conservation of momentum term gave me a minus sign. So then I can take the, this is a 1i here, this I can take u1i out. So I have 1 plus m1 over m2 over u1i is equal to 1 plus m1 over m2. This is a 1f, u1f, like that, with absolute values. These two terms cancel. And I wind up with u1i is equal to u1f with absolute values in it. So let's get rid of these like this. So the size of u1i has to remain the same in the center mass frame. And we can do the same thing to find u2i versus u2f, and we'll find out that they are the same size. But in order to conserve momentum, you actually have to have the signs flip. So, so once you go back and check the signs in the momentum setting, the final thing we'll find out is u1i is equal to minus u1f, and u2i is equal to minus u2f. So what's that mean? That means if in the center mass frame, I have one guy here and the other guy here coming in, then they hit, and this guy has to turn around and go back out with the same velocity, and this guy has to turn around and go out with the same velocity. So if this one is smaller, then he has a bigger velocity in the center mass frame. So this velocity is the same as that velocity. So they come in and then they just turn around and go back out, but with the same speeds. Does that make sense? So that's why the center mass frame is nice, because you just have to know what the velocity is when it comes in, and you'll know what it is. It has to come out the same thing. And so yeah, so there's it makes it for elastic collisions, it's really nice that way. So so now let's compute the center of mass. So if we had the initial velocities here, we know the final velocities immediately, no calculation involved actually in the center of mass frame. So what's the center mass velocity for this system? So the center mass velocity, we never actually computed it yet, but we can compute it now. So remember, you sum the masses, and then you multiply the masses by the initial velocities in the lab frame. So for this problem, I set V2 initial velocity to be 0. So it would be this if this weren't 0, but since we have 0 in this one, we can just get rid of it. So this is the center of mass velocity. So so now that I know the center mass velocity, I could figure out what the velocities are in the center mass frame. So let me show you how to do that. So U, which is the velocity in the center mass frame, is the velocity in the lab frame minus the center mass velocity. So I just computed the center mass velocity. So if we calculate this, it turns into this m2v 1i over m1 plus m2. And so now I can go backwards and say, what's the final velocity in the center mass frame? So that's u1f. It's just the opposite sign of this. So it's minus m2 v1i over m1 plus m2. And now I know, so now I know the velocity, final velocity of the first mass in the center mass frame. Now I can go back into the lab frame. So v1f, I just add in is u1f plus the center mass velocity. So I subtracted the center mass velocity to go into the center mass frame. Now I add the center mass back to go back into the lab frame. And so I'll add this to that. Okay, so this will be m2v1i over m, that's this, plus this plus M1V1I. Then there's a sign. Oh, right. So this is, I got to add this with a minus sign, so it's this. Okay? And so that's equal to M1. It's really hard to write down here. It's equal to M1 plus minus M2 over M1 plus M2 times V1I. Okay? So that might recognize as the same thing we computed at the beginning when we solved the problem in the lab frame. So this is another way to solve the problem. You figure out what the initial velocity is. You compute the center mass velocity, figure out what the initial velocity is in the center mass frame, flip it because you're in the center mass frame, and then figure out what the lab velocity is by going back into the lab frame. And you get the same answer. So just sometimes that's easier way to solve these problems. So any questions about that? The usefulness of the center mass frame? No questions. Okay, well, if you have questions, butt in. So, okay, so that's this setting, non-relativistic elastic collisions in one dimension with two masses. So we're going to stick to the two masses, but now we're going to do, oh, there's a mistake here. We're going to do anelastic collisions. I have a title. So I'm going to change this. They're not going to be elastic. So kinetic energy is not going to be conserved. And we're going to let the particles stick together. So what's this collision look like? So I have V1I and M1, and it's going to hit another mass, M2, V2I0. We'll start with that one also being not moving, stationary. And then they're going to stick together. So what comes out is two guys like this, and they're moving together. So since they're stuck together, what's coming out has to be at the center of mass. So this together is one mass. So conservation of momentum means the velocity of the whatever's leaving is actually the center of mass velocity. So that's convenient. So if we want to figure out what velocity they leave after the collision, all we have to do is compute the center mass velocity. So VCM is M1V1I plus 0, because this one is over the sum of masses, M1 plus M2. And that's it. So this is this velocity, and this follows from conservation of momentum. So that's what the problem looks like. So what does this problem look like in the center mass frame? So in the center mass frame, so we have UI, and this one is not as fast because I've drawn him as if he's more massive. U2I. And then so they're sticking. And since they're sticking and we're in the center of mass, afterwards we just have this, and they're not moving. So this is velocity 0. So U is equal to 0. Final velocity of the combined thing is 0 in the center of mass frame. So you can think of them, they just kind of go like this, and then they stick, and then they stay there. That's what the problem looks like in the center of mass frame. So, So before we found out that the final velocity was the center of mass velocity. So let's look at now what are the velocities in the center of mass frame. So the kinetic energy prior to the collision looks like this, V1I squared. And the kinetic energy after the collision, so this is before collision. So because we're doing an anelastic collision, energy is not conserved. So some of it sticking means some energy goes into heat or radiation or something like that. So before the collision, that's the kinetic energy. So this is the initial kinetic energy. So the kinetic energy after the collision is 1/2 m v center mass squared, because it's the total mass times the center mass velocity. And we can use our previously calculated value for the center mass velocity to figure out what it is. M1 squared over M1 plus M2 squared times V1I squared. And this, so this is less than that. Oh, right, or then I have to multiply by M1 plus M2, because this is V center mass squared. That's the total velocity. So this thing cancels off that. So that's what it looks like. Does that look right? Yes, that looks good. And this thing should be smaller than that. And in fact, let's calculate it. So the change in kinetic energy is the initial minus the final. And I'm just going to subtract these guys out. And what we'll get, if you do this calculation, is this. V1 initial squared. So you can see both of them have the V1 initials. But I have to multiply top and bottom by M1 plus M2 in order to, and then this gives an M1 squared, which cancels out, I think. And then you've got a factor left here. But the answer that you get is this. M1 plus M2. So if you look at this, you recognize it actually. So this is the same thing as mu times the velocity difference. So we could write this as 1/2 mu u diff squared. So remember, kinetic energy for a two-body system, you can write it as the translational kinetic energy, which is that of the center of mass, plus the relative kinetic energy, which has the reduced mass times the velocity difference squared. This particular problem, because when it gets together, it just sticks. It loses all the relative kinetic energy. And so the change in kinetic energy, which is the amount of energy lost, is equal to the internal kinetic energy term. So this is that makes sense? So when we showed before that you could always write kinetic energy as a sum of these two different terms is useful here if you want to know the energy loss. So for all sticking problems, you essentially are losing the relative kinetic energy, because that's when the center of mass has to stay fixed because of conservation of momentum. So the translational kinetic energy doesn't change. Okay, so that's that topic. Non-relativistic anelastic collisions where two masses stick together. So any questions about that particular example? No questions? Okay, so let's move on. So far we've been doing 1D. So now let's go up a dimension. So let's do non-relativistic collisions in 2D. So, so what are our conservation laws? Our conservation laws are momentum, total momentum. Total momentum. So this says P is equal to M, velocity of center mass. That's another way of writing the total momentum, MI, VI. And these are the velocities. And so this is conserved. So that means it's the same before and after the collision. So are there any other conservation laws? So if it's anelastic, then the total kinetic energy is conserved before and after the collision. So momentum, we have 3 degrees of freedom. If it's a 3D collision, and we have 2 degrees of freedom if it's a 2D collision. Kinetic energy is a signal equation. So you can kind of get the feeling that you don't always have enough information to figure out everything that's going on in a collision. So, so often we'll have problems where we're trying to figure out, you know, what are the missing pieces of information. We have to measure things like, often if you have a piece of the problem you don't know, like I'd like to know something about the mass of one of the particles that comes out, you need to measure a lot of the outputs from the collision in order to figure that out. And that's kind of a theme in particle physics. They try and track a lot of particles to find the particles that they have trouble measuring. And that helps them understand the underlying physics that's going on in the collision. So, so when you think about this, there may not be necessarily enough information to solve all possible collisions. So if it's elastic, you have this other constraint that sometimes helps. So let's do another example. So I put this in 2 dimensions, so we're going to do a 2-dimensional thing. Total momentum is always conserved. So, and so last time we did 2 particles sticking together. So let's do the opposite. We'll have a single particle that disintegrates. So let's do disintegration. It's making so much noise. Maybe if I put this up. That's much better. Okay. In duty. So I'm going to do a disintegration problem. So, so we have a mass coming in, and it's got velocity v. And let's do a coordinate system y, x, and we'll have the disintegration happen at x equals 0, y equals 0. So this is where it disintegrates. Okay, so this is before. And afterwards, what happens? We've got a bunch of masses. It's disintegrating into more than one mass. So here's M2. We'll go out this way with V2. Yeah, V2. And we have, so here's, let's draw the axes again. Y, X. And we've got an M1. And M1 is going vertically with V1. And we have another particle, M3, that's going out at with velocity V3. And M3 is going out at angle theta. Okay, so this is final. So we'll assume that no mass is lost. So no energy went in to say radiated particles or anything like that. And this is still a non-relativistic setting. So let's So since no mass is lost, M3 is equal to M minus M1 plus M2. So we'll assume that the sum of the masses afterwards is the same as the sum of masses before. And we're going to be able to measure, so we know the total mass, we know the total velocity, we know, so let me list of what we're going to know, because so we're going to find out the things that we don't know. So we know M1, M2, M, which means we also know M3, and we know V, the initial velocity, and we know V1, and we know V2. So the things we don't know are, we know the direction of V1 because it's vertical, and we know the direction of V2 is horizontal. And the thing that we don't know, so these are all known. So let's call them known. The things that we don't know, unknown, will be V3 and theta. So the size of this vector and the angle theta. So let's now solve this. So we're going to solve for V3 and theta. Okay, so that picture we kind of need, maybe I'll move this picture up here. So yeah, let's just erase this, and I'll erase this. But I'm going to remind you that the initial picture is M and V, okay? That's the initial picture. So, so let's use conservation of momentum. So momentum, so the total momentum, V, right, over the particles. So let's take Px. That's going to be the x component of momentum. So initially it's m times v. And in the end, so we need the horizontal component. So v1 and m1 are going vertically, so there's no horizontal component. But v2 and m2 are giving me a horizontal component, but it's negative according because the x-axis I defined as positive in the horizontal direction. And I also have a component from m3 v3 plus m3 v3 cosine theta. So if theta were 0, then I would have a positive horizontal component. So that's why I have a cosine there. So that's the component of the momentum, horizontal momentum. Now let's look at the y component of momentum. So the initial velocity was only horizontal, so it's 0. And the final one, we've got m1v1 because that's this component, and we have a component of m3's velocity sine theta. Yeah, that looks good. So we've got two equations now, and our unknowns are v3 and theta. So we can solve these for v3 and theta, because that's what we wanted to do. So the easiest thing to do is move everything that doesn't involve v3 onto the other side of the equation. And so I'll do that. We've got m3 v3 cosine theta is equal to m v plus m2 v2. And now I'll divide by m3. So let's divide by m3 like this. And this one will be v3 sine theta is equal to m1 over m3 v1. So that's nice. And now I can square both sides. v3 squared, sine squared plus cosine squared is 1 is equal to 1 over m3 squared times mv plus m2 v2 squared plus m1 squared. So that's the answer. So that's actually the expression. We can take the square root of this if we want the final answer. And using these two equations, we can also solve for theta. So theta is a tan 2, where I just take sine, cosine. So this is m1 over m3 v1 comma. And actually, I don't really need don't really need to worry about the m3 because it'll cancel out in the ratio. So this is mv plus m2 v2. So using the a tan 2 function, we can find the angle. So that's what we wanted. We found the two unknowns. So see how that's kind of done? We just use conservation of momentum here. We didn't use energy at all, but we had a lot of information after the encounter. So that gave us enough information to solve for the few pieces that we didn't know in the problem. So you'll see this theme in particle physics again, where the goal is to find out things you don't know using products of incoming and outcoming, the information you have from the incoming and the outcoming particles.
Professor?
Yes?
I have a quick question. So in the last expression with a tan 2, what is the symbol between m1 v1 and mv plus m2 v2?
Oh, this is a comma. So
okay.
I don't know if you remember that it's handy to have this function a tan 2, which gives you the right quadrant of things. So I tend to use it. I mean, you could just have a tan of the ratio, and then you just have to check that you get the sign right. So every time you take, you use inverse tangents, there's always this issue of being off by pi. So
All right.
yeah.
Thank you.
So this is just a function of two arguments. It's commonly used in computer science because it always gives you the right quadrant, for the angle. So
all right.
Yeah.
Thank you.
That's why I write it short. It's shorthand. It also saves me worrying about the signs, right? So shorthand. Yeah. So if you guys remember, a tan 2 is a function of two things. One of them is y, the other one's x. It's usually when you're doing the when you're trying to find the angle. Okay, so so that's an example, non-relativistic collisions in 2 dimensions. And you guys will have a problem set. So this week you've got center of mass, then next week is a break and the problem set's the week after you'll be working on the collision problem set. But there'll be a couple 2D examples where you're worrying about, you practice writing down the equations for conservation of momentum, including angles for the velocities coming in and out. So far you've only done non-relativistic collisions. So what happens when you have relativistic particles? So I'm not going to do any examples, but I'll just write down what you can think about how you generalize. Relativistic collisions. So it's convenient to work with a 4 vector. So this is the energy, and if you had a bunch of particles, the energy would be a sum of the energies of the particles. And this is the momenta, and there's the total momentum. So this is total energy, and I can write that, yeah, it's a sum over all the particles of the energies of the individual particles. And when you have relativistic particles, this is gamma m c squared, where these are the Lorentz factors. So once you have defined your reference frame, you can compute the Lorentz factors for each particle. This is c squared, and these are the rest masses. Those work for massive particles, but we could also have photons or massless particles in your in the total energy. So photons can come in and out. So you can also add in the energies from photons, for example. So this would be sum of H nu I, where I goes over all the photons. So these are the massive, and you can add in energies for massless. So the total momentum is the sum over the momenta of the individual particles, and these are all vectors. And these for massive particles are gamma MIVI. And you can also add in, H nu over C for each of the photons, for example. So we had a formula for momenta of photons. So you can see how you can add these all up. The Lorentz factors are for each specific particle. And this 4 vector, the sum of it is conserved. So you get the same total momentum as a vector before and after the collision, and the same total energy before and after the collision. So this is conserved. So when we were doing collisions, non-relativistic ones, and we had like particles sticking, energy went into things like heat. But if you're doing like relativistic particles, instead of worrying about heat, you have things like radiation coming off, and sometimes very fast particles. So some energy could go into excitation processes. So you could have what's called inelastic collisions, where say like a nucleus winds up vibrating after the collision. So deep inelastic scattering involves excitation of degrees of freedom of the nucleus of the particle. And then it would look like, if you're counting all the particles, it would look like you're missing some energy, but really some of it's gone into excitation, and it may eventually decay and radiate that energy. So relativistic particle experiments, you assume all energy, you're not losing any energy, you can keep track of where it's going, is usually the assumption. So we could do problems like this involving Lorentz factors of massive particles and keeping track of energy for radiation. Just like we found with non-relativistic collisions, often it's convenient to go into a center mass frame. So what's the center mass frame for a relativistic setting? So the center mass frame in the relativistic setting is the velocity that gives you 0 for the total momentum. So does that make sense? So you can find a frame, you can transfer into some frame that gives you a 0 total momentum, and that serves this purpose of the center mass frame. So it can be quite convenient in these types of collisions when you're calculating outcomes to work in the center in that frame. So this is like the 0 moment. It's equivalent to the center mass frame. Okay, so why are these? So this kind of foundational physics here. So I'll give you an example of an important experiment that was done with collisions. So this is the Rutherford gold foil experiment. Rutherford gold foil. And I think the name of the experiment is Geiger Marsden. So what's the experiment? So the experiment is you start with a radioactive source. And what's coming out of this source are alpha particles. So alpha particles are helium nuclei. So 2 protons and 2 neutrons. So these are helium nuclei. But there are radioactive materials that spit out alpha particles. And the alpha particles were let to hit a gold. So I can't really, don't have any yellow, but let's use red. So this is a gold foil. And gold, yeah, why'd they do this with gold? I think they did it with gold so it wouldn't tarnish, and so they were sure that it was gold and stayed gold. And then what comes out, what comes out are some electrons. So the alpha particles, I think it's electrons, right? Or is it, no, it's not electrons, it's the alpha particles. Not electrons, particles. So the alpha particles come out, and then they hit a screen. And that screen, when an alpha particle hits the screen, photons come out. And there's a camera or somebody looking, because these were experiments done a while ago. And you could, so you can adjust where the screen is. You can put the screen on this side, it doesn't have to be on that side. So take gold foil, and when they were doing the experiment, they didn't know what was in it. You know, they didn't have this picture of atoms and things like that. So people's impressions of solids was they were really uniform. But when they did this experiment, what they found is that almost all the alpha particles just went straight through and didn't even notice the gold foil. So most of the gold foil is empty. There's like nothing in it. Alpha particles just zip right through, didn't hit anything. Some of them hit something and they recoiled like almost backwards. And so the distribution of the angles was really extreme. So whenever an alpha particle hit something, it had an extreme change in its momentum. So the way to interpret that, so since it could bounce backwards, the way to interpret that is the thing that it was hitting was really heavy, like a lot heavier than the alpha particle. So this experiment revealed that the gold nuclei were really heavy and really small compared to the amount of space in the gold foil. So you can see how the interpretation, so instead of measuring the velocities of the alpha particles after the collision, they measured the angular distribution, and that was sensitive to the mass of the nucleus and the alpha particle. So it involves a little bit more work because you have to compute the distribution of angles to interpret the experiments. But the overall trend is that these alpha particles were hitting something really heavy, and the fact that most of them went through without even having a collision tells you the cross section is small. Like, so that cross sectional area of each thing in here is small. So that gives you this idea that nuclei are actually small, and you can estimate the size of the nucleus from the number of particles that just went through. So yeah, so that's why that experiment is important. So these are alpha particles coming off from a radioactive source, so they may not be hugely energetic. Later experiments, you could accelerate particles to higher energies, so that means they have big Lorentz factors. And when they hit the nucleus, so with the alpha particle experiments, there wasn't enough energy to excite internal degrees of freedom in the nucleus. So later experiments studied this phenomena called deep inelastic scattering, where a lot of energy goes into exciting the nucleus. I don't know if you guys Doug Klein, he retired a couple of years ago. He studied for spin degrees of freedom excited. So he knew spin dynamics really well. It was one of the things that's really clear in his book on classical mechanics, is the spin, angular momentum, and precession of non-round bodies and things like that. And the reason he was very good at doing that is because he was interpreting deep and elastic scattering of a nuclei in terms of excited rotational degrees of freedom. Kind of interesting to look at. Okay, so that's the Rutherford gold foil experiment. So other experiments that were important historically involve beta decay. So what's beta decay? Beta decay. So beta decay. So let me just write down a reaction, and then I'll tell you what the beta is. So we start off with a carbon. So carbon, what's here? Oh, this is a 6. So this is the number of protons. This is the number of protons plus neutrons. And so I have a neutron here. So you see the 14 is the same here. So the number of protons plus neutrons is staying the same in this reaction. So this carbon is turning into nitrogen plus an electron plus something else. So yeah, so really what's happening here is we've got a neutron going to a proton plus an electron plus an anti-neutrino. In the nucleus. So if you have like a big pile of carbon and you just let it sit for a while, particularly carbon 14, every once in a while this will happen, and the electrons are called beta particles. So when you say beta decay, this is a decay process that emits beta particles. And you can see, well, so there's certain things in these particle reactions that are conserved. So this is neutral, this is positive, and that's negative, so they cancel out. So you can check that charge is conserved in the reaction. And then we have, so this involves an electron, so it's a lepton. Lepton number is also conserved. So this is an anti-lepton because it's an anti-neutrino. And so +1, -1, and lepton number, those cancel out. So you can look, this involves leptons. And because it involves leptons, that means it's a weak process. And turns out a W- boson is involved in the reaction, mediates the reaction. So nuclear processes that involve leptons are mediated by the weak force. So when they first started looking at beta decay, you can detect the electron. It's not necessarily hard to detect the electron. You can see the nitrogen maybe. So these are easy to see. The neutrino they're really hard to detect because they don't interact much, and they're nearly massless. For a long time, people, not until quite recently, people were aware that it had mass. So this thing, nobody knew what it was, and so it wasn't easy to see. So how did they figure out that there was something like a neutrino involved? So what they were doing is measuring the kinetic energy distributions of the beta particles. And Lisa Meitner and Odo Hahn in 1911 and Jean Daniels, I don't know how to pronounce his name, in 1913 saw lines in the spectrum, the energy distribution spectrum. And when they looked at the distribution, it was in contradiction to the conservation of energy. So there was some energy missing. And so because there was energy missing, people were trying to propose, well, what happened? Where did it go? And one proposal was that it went into a mysterious particle that had to be neutral, partly because of the charge conservation, but also, so first, I think it was Pauli proposed a way to resolve this problem with a neutral particle that wasn't seen, that he called the neutron. But then later on, the neutron word was used to describe a different process. And so Fermi renamed the missing particle the neutrino. So the hints that there had to be these particles that people didn't know about yet came from looking for where missing energy was in order to explain their data. So, and then how do you confirm it, actually? So, so a few further experiments then tried to look at the recoil of a particle once it emitted the neutrino. So there are additional experiments that needed the same particle to explain the phenomena. So, and then, you know, trends like the fact that these all involved leptons. So that's where, and then because the beta decay takes a really long time to happen, so it has to be really weak force. So you can see this is like the development of this standard model picture that involved these early experiments where they were using conservation of energy and momentum and collisions or collision-like settings. In this particular case, you're just waiting for some reaction to take place, but using those concepts to propose new physics, because if their physics wasn't there, then they had a problem with the conserved energy or the conserved momentum. Okay, so we're out of time, but does anybody have any questions? Otherwise, we'll sign off then, and I'll see you on Thursday in Hoyt. Oh yeah, there's the IT people claim they figured out the solution to our sound problem. So we'll see. Maybe we'll have better sound for the online. Finally, they say they know what the problem is. It had to do with the camera. One of the cameras was interfering with the data rates, apparently. Anyways, I'll see you guys on Thursday.
Thank you.
Thank you too. Bye.
Thanks, Professor.